Good morning, if anyone is out there. Yes, we're live. Good morning, and welcome to today's Green Star Green Star case study webinar. I'm going to be talking about a test I did back in February in Sydney on a building called the Workshop. So yes, CPD, get in touch if you need your certificate for your Green Star Sustainable Development Points. The email address is on your screen. So let's begin. This is a beautiful render of the Workshop in Piermont in Sydney. This is the building that I tested earlier this year, right before COVID struck, which was lucky that we got this done in time, because that would have been a bit of a disaster, wouldn't it? So here is a bit of a timeline as to how this project unfolded. There was about 5.5 months between the time that the builder first contacted me and when we did the test. So ideally, as you would know, if you'd watched my other webinars, ideally the timeline is much longer than that, particularly for these large commercial projects, or any project really, but ideally, you know, someone like me would be involved in a project like this from design stage to try to avoid some of the issues we came across while we were doing this test. So I was contacted by an Icon representative in August last year, and I managed to get 2 site visits in between the first, me being in Adelaide, then being in Sydney. I managed to get 2 site visits in between their first contact and the test date, which was very beneficial. It allowed me to see where they were at with their project and, you know, lay my eyes on what they were actually doing and point out a few, you know, obvious things that could potentially be fixed up before test day. So that was in September, and then again in December, right before Christmas. They decided they still wanted some advice on how they could go about preparing the building as best they could before test day. Icon with the builder, and they were very on board with everything that we were doing right from the start, very interested in doing the best they could. They didn't know anything about air tightness testing before they came to me, and they were really open to learning. So they wanted as much information as they could. So they took on everything that I was offering, which was great. So the testing was late February this year. So when they contacted me, the first thing I did was the red pen test. I identified the air barrier and had to work out basically what the test zone was going to be, because this is a mixed use building. So there was gyms, cafes, office spaces, childcares, a lot of different things going on. So we needed to work out exactly which part of the building we were going to test and work out where the air barrier was going to be. So we tested 9 levels, and this was made up of 2 ground levels, like a lower ground and an upper ground. There was also a mezzanine in there, and then we had 7 office levels above that. So on the lower levels, we only tested a portion of it. So you can see here, this is the lower ground level. I'll use the proper screen. This is the lower ground level. This was all cafe space. And in our initial plan, we were actually going to test this space, and we looked at all the external doors and everything that was going on in this area. And there were quite a few areas that needed attention in external doors in these commercial buildings that are generally not designed for air tightness. So there were a few issues around the doors, and there was also some external vents there and things like that needed to be taken into account. In the end, we only ended up testing this small section here. So this was an atrium. This blue section here was an atrium that went all the way up to the top of the building, or there was a smoke exhaust at the top. So that was beneficial in that it allowed the air to be spread through the building quite easily. As you can see here in my little picture, we had 3 fans placed at the rear of this little section, and without that atrium, it would have been quite difficult to get the air from the lower level up to the higher levels. We had quite a large amount of difficulty finding appropriate doorways to put the fans in to spread the air distribution out across the building, and this was really the only option we had in the lower section of the building. So having the atrium there was quite fortunate for the air testers. Next level up, this was the mezzanine level with just, there's like an entry point on a different side of the building. Oops, wrong way. And then we keep going up. So there was, hang on, mezzanine, and this was the childcare centre here. That was not completed yet, so there weren't any external walls in the childcare centre. So, and being a different class of building under the Green Star rules, they have different targets and things like that, which can get confusing. So we excluded the childcare and the cafe in the end from the test zone. Going up, this section here was some boutique offices. So all of this, the other levels were all open plan office spaces, and these sections here were all individual compartments. And there was no way we could get air from those boutique apartments through to the rest of the floor plan, the rest of the level. So we also excluded those offices being individual compartments. It was also decided that the best way would be to test all of them individually. We didn't end up doing that. We ended up deciding that the best way to test this building was just to test all of the office spaces and those lower ground levels in one go. And that was going to give us the best indication of the performance of the building overall. Going up, we had a standard floor layout in the mid levels, and then we get up to level 6 and level 7. So level 6, we had we placed 2 more fans on level 6, and then up on level 7 we placed 3 fans. So the fan load was quite concentrated on the upper levels because, like I said, we had a lot of trouble with doorway access. There weren't doorways on the lower levels for us to use. But again, because we had the atrium, spreading air across the building was made quite easy, with the exception of level 6. Level 6, we had some issues because on level 6 and 7 there was a glass barrier around the atrium. So on the other levels, the atrium was open, and on level 6 and 7 there was a glass enclosure. So we had to get the air from this section here through the doorway. There was a doorway that went into the atrium and down some steps from where we had our fans, and that's the only access point we had. We had one 820 by, I think it was 2.4 doorway to get air from those 2 fans into the atrium, and that created a problem. We had a significant pressure drop from one side of that door to the other side of that door. So what we ended up having to do was actually open up the lift. We had to open up the lift doors on the other side of the level, which then set off the fire safety mechanisms, and the fire curtain came down. So there were these sorts of logistical issues that happened on the day, and we got around it. We had some really helpful ICON representatives on site who helped us prop open the fire curtain and keep open the lift doors, and we managed to get the equal pressure that we needed across that atrium area in order to carry out the test. But it was quite amusing on the day. Level 7, this was primarily plant. This was primarily the plant room. So we had 3 more fans in, and we didn't end up putting them there. We ended up putting them over here somewhere on near the balcony, which was much more open to the rest of the floor level. So the air barrier, we obviously don't include unconditioned plant areas in our test zone. So the air barrier was around only the conditioned office space. And here we had a unconditioned hallway, and this was the smoke exhaust area. There was 3 very large fans here. So our air barrier excluded all of that unconditioned space. Moving on. Next. Have I got the right slide? Okay. So from the red pen test, once we've identified the air barrier and the test zone, we work out how large the building is. Generally, this can be done just using PDF Bluebeam software, but for a building this large, I like to create a 3D model to make sure it's really accurate. So this was the 3D model I created of the building that we tested, the workshop. Got some nice section drawing so we can see kind of what's going on inside. The program that I use was SketchUp. It's a quite simple program to use, and it gives me calculations on volume and also surface area or envelope area, which is really useful because I need both of those numbers in order to get results. So in a commercial building, we generally only use the envelope area to determine the size of the building. In residential settings, we use the volume of the building. In commercial, we use the envelope area, or the surface area of the walls, the floor, and the ceiling or the roof. I've put both numbers on here today. So the volume of this building was 60,000 cubic metres, or nearly 61,000 cubic metres. The envelope area was 11,620 square metres. So the difference between those two numbers is quite large. And the reason that is relevant is because we use those numbers to create a result at the end of the test. So we take the amount of air that's required to pressurise the building to a certain level, which is 50 pascals, and then we simply divide it by the size of the building. So it's it's really simple maths, really. But if we use the volume of the building compared with the envelope area of the building, we get very different results. So for example, if this building needed 100,000 cubic metres of air to pressurise to 50 pascals, if we divided that by the volume of the building, the result we get is 1.64 air changes. If we divide that 100,000 cubic metres of air by the envelope area of the building, we get 8.6 cubic metres per hour per square metre as the result. So 1.64 and 8.6, there's a big difference between those two results. And if you're going, for example, for, best practice results, you would achieve that with an air changes result. You would get if your target was 2 air changes on a commercial building, it would appear that you would achieve your best practice targets. But in reality, the way that, because the volume of a commercial building is so much larger than it would typically be in a residential building in comparison to the envelope area, that the volume is not an accurate way to normalize the air that's required to pressurize. It's not an accurate way to get a result out of an air tightness test for a large commercial building. What we're really measuring is how much air is leaking out of every single square meter of the building and testing the facade. So that's why across the globe you'll find that with commercial testing you won't find air changes used. It's also not a very good way to compare buildings because the numbers are so vastly different between residential and commercial style buildings. So in a commercial setting we always use cubic metres per hour per square metre. That's the moral of that story. I hope that made sense. It can be a little bit tricky to explain. So as you can see, I've got a photo here of my first site visit in September last year, and the building was well on its way to completion. The second site visit, they just had a few minor things to fix up. So I was, as I said, involved in the project in a very late stage. So this is something that the builders, this is a lesson they took out of this project for next time. So these are some pictures of their large exhaust fans they had in their smoke room on the top floor on level 7. If you remember a few slides back, I had the top floor and then I showed you the corridor that went to the smoke exhaust room. These dampers were a significant issue in the test because this section here, this grill, was open to the atrium, which was then open to the smoke exhaust. So the unconditioned smoke exhaust area was completely open to the conditioned office spaces. This wouldn't have been necessarily a problem, except that the dampers that were used on the back of these extremely large exhaust fans didn't completely shut. So the photos I've got here, you can see they're not fully airtight exhaust dampers. You can see daylight coming through quite a lot of that damper, which then opens out straight into this louvered wall. So when we depressurized the building, there was air coming in through this grill, in through these dampers, through the fan and into the atrium. So there was a large amount of airflow coming from this smoke exhaust room. there was a wall, and I haven't got a photo of it, but there was a wall that actually attempted to separate that section around, sort of the fans came through the wall, and the wall attempted to separate the unconditioned smoke room from the conditioned section, but the dampers unfortunately weren't super effective. So from an air tightness perspective, this compromised the results of the test. So here's a picture of where the smoke room is located in the building. This was the atrium, all the way up here, and then the air just went straight, in and out of here quite freely. This is a closer version. So this is the grill, and this is the wall that I mentioned. That did actually reach the ceiling. So yeah, through here we had quite a bit of air movement. This was the corridor that led to the smoke area. So this is not when the building was at completion, but this is a photo I took as an indication of something that the builders needed to address before the test day. Again, because all of that area was open to the atrium, the best solution was to actually fix up these external areas. So by the time I got there on test day, this was improved. It wasn't perfect, but it was definitely an improvement on the previous site visits. Issues such as this, a door with, a 1/2 inch gap in the door leading to an external area, that's a fairly obvious thing, and also quite easy to fix that one. This is the corridor that led to this picture here. This is the corridor leading to the smoke exhaust area, and relates to this picture here. So just to give you an idea of the location of what I'm talking about. They had some issues addressed at the wall roof junction at their parapet. So that still proved to be a problem on test day. So that was a little bit more difficult to fix. Here we have the cafe doors that I was talking about earlier. We ended up excluding the cafe area, but on my site visits we were still including it. So the pictures here indicate the issues that we identified with the doors. They had these beautiful big doors that were going to fold up to sort of for that alfresco dining area, but they had some air tightness issues. They all had a gap, yay big around the entire perimeter of the door, and there was two large doors, so that little gap adds up to quite a large gap when you think that it goes the whole way around the door, and there's also gaps in between the panels. So that was something else that gave us a bit of trouble, because there was not really much that could be done about that. The lift shafts. So lift shafts are extremely tricky separating conditioned and unconditioned spaces, because they generally go from basement to, office levels and things like that. This is a view here standing on one of the office floors, and this was the gap between the floor plate and the lift, and we could see directly down into the levels below, the basement levels below. They also had a beautiful big glass lift that wasn't sealed along, this door here, this junction here where the doors close, wasn't sealed. So that was, that's not the seal, that's the wire that holds the lift. But anyway, the doors weren't sealed. I haven't got a photo of it here, but the doors didn't have a seal when they shut. So again, free-flowing air coming up through that lift shaft. Some unfinished sections identified on the second site visit, stuff that just could easily be, sealed up with some expanding foam or some silicone. So yeah, this was all unfinished stuff. But by the time test day came around, some of it had been addressed, but not all of it. And that's another thing, is when you're getting a test done on a commercial building or any building, we tried to push the date for this test out as far as we could. But when it comes to the end of a project and there's so much going on, there's people rushing around trying to finish stuff off, handover date is looming, everyone's getting quite anxious about the end of the project. And there's lots of people on site trying to do what they have to do. And then we have to come on and basically everyone has to kind of stop what they're doing. So scheduling gets really difficult when you're trying to find a time for us to come on site. So our work is generally done on weekends or overnight when there's no one on site, because we just get in each other's way. But yeah, scheduling needs to happen as late as possible. This one was pushed forward a little while, so we were there probably a touch too early, because there was still little things like this that weren't finished. So something to think about if you are going to get an air tightness test done is schedule it as late as is possible before handover. Here's some more pictures. Test day finally came around. All the gear got dropped off. We freighted it from Adelaide, which is quite a simple process, and set all the doors up. Here they are, all looking very nice and red and beautiful. There's a lot of wires, a lot of hoses, a lot of stuff, a lot of Ethernet cables, just stuff going everywhere. In a building this size, we tend not to use Wi-Fi signals. You can use Wi-Fi signals to connect up all of the manometers to the laptops, to each other, to everything. But in a building this size, the signal's very weak and it's not reliable. You can probably only really do that over a double-story building. By the time you get into 2, 3, 4-story buildings, you need Ethernet cables for a reliable signal. So that means a lot of tangle, which takes a long time to set up. There's a lot of different things going on. So this is just to give you a sort of an idea of what goes on. This is my colleague Sean Maxwell. He's lowering an Ethernet cable down the atrium down to the lower levels to connect up the lower fans to the fans on level 6. And this was the door that we had the trouble with. He's standing on the other side of the door on level 6. This is where the pressure drop occurred that we had to try and fix using the lifts over here. And that's just a pretty picture of their beautiful greenery in the atrium, which was nice to look at. The preparation of the mechanical systems was done by Icon. So we were there. That Icon was there with us, and because we didn't have the appropriate roof permits and things like that, Icon were there to do all that sort of stuff for us. So they got on the roof and taped up all of the vents on the roof system, because when you're testing for Green Star, you want to be eliminating any leakage that's as much as possible going through the ducting, because that's not we're testing the building envelope, not the mechanical systems themselves. So we're testing what air is leaking in and out of the walls, the floor, and the roof, not out of the ducting, typically. So all of this was taped up. So the result of this test in the end was, and I had permission from the builder to release the results. The result was they got a permeability of 15.45 cubic meters per hour per square meter. So they achieved, under Green Star, you have to get a result of 20 in order to get 1 point. And for an office building, you need to get 5 for 2 points and 2 for 3 points. So they were still well within, despite coming to us late in the game, despite knowing nothing about air tightness testing, they still achieved the point that they were after for this test. So for all of you out there who are doing Green Star projects and avoiding air tightness because it's scary, you don't know anything about it, and you're worried that you'll fail and you're worried that you'll waste the money and the time, etc. My sort of opinion on that would be, don't be afraid. Failing an air tightness test or getting more than a permeability of 20 under the version 1.2 of the Design and As-Built guidelines, that version. There is a new version, but under those thresholds, getting 1 point is not super difficult, and it's also a really, really good learning curve. So I would recommend it, not just because it's what I do for a job, but because it's not that scary and it's not that difficult to achieve. So it's likely that you will still get your point even if it's unknown and scary. So we tested the entire building on this project. Sometimes, quite often with large projects, because of the state of air tightness testing in Australia, it's still quite new here. Not a lot of contractors have got enough equipment to test whole buildings. There are a few people who do, but for the most part, the equipment's really expensive. So people have got one or maybe two fans for the most part. They can do residential testing in small commercial buildings, but for the larger commercial buildings, what contractors will often recommend is a compartment test or a smaller section, a couple of levels. And if you watch my other presentation, that explains a little bit about what compartment testing is and the difference between compartment testing and whole building testing and all the other different types of testing. If you've watched it, you will know that compartment testing, although it's allowed under Green Star, it doesn't give you a number that you can use. So the compartment testing is not testing all external envelope, and the numbers that you use to convert the result are skewed. So go and watch that presentation if you don't know what I'm talking about. But we were able to test this whole building in one go. So this number, this 15.45 cubic meters per hour per square meter, we know that that is a very good indication of the performance of this building as a whole, because we got to test the whole thing, not just a small portion of it. So it's a number that you can trust. And it also means that we can compare this building with buildings all over the world, in terms of air tightness, for education purposes, for research purposes. We can compare this building to other buildings and sort of get an understanding of where it sits. And as the numbers of testing increase across Australia, we can get a better idea of where Australian construction sits in comparison with our international counterparts. So the whole building testing is really, really important. So if you're getting a quote, make sure that you understand exactly what is being quoted. Something else that was really good that we were able to do while we were in Sydney was actually partner up with the Green Building Council of Australia, and we conducted a site visit. So we had some Green Star professional, GSAPs, Green Star accredited professionals, come and we did a demonstration for them. So we also had some GBCA representatives there to learn about what it is. So that was really exciting for us, because the more people that know about what goes on during a test and what it all means, hopefully the more testing that will go on and the better buildings will become over time, because the point of Green Star is to make better buildings. And air tightness is a really important part of that process. So that was really fun. I got a bit of feedback from the ICON representative that I was dealing with throughout the whole process. And her feedback was that if she was presented with an opportunity to do this sort of testing again, she would communicate the intention to undertake air tightness testing to an architect and all subcontractors at the beginning of the project. The ability to make design changes at low expense or no expense at all is highest at the beginning. So what we always say is to get air tightness testers involved at the beginning. It needs to be part of the process, just like any other design construction element. That was the biggest lesson that she took out of this whole process. So it was, validating for us that they were, one, so open to learning, and two, took out of it the things that we continually say over and over again. So that was really great. All in all, it was a really great experience for us and for the builder. So that's it for my webinar today. I hope you are all enjoying what we're putting out there. We've been getting some pretty good feedback from everyone, so we're really happy about that. So today is the 14th. This is my session here. Tomorrow we've got designing smart walls, some information on the commercial code changes if you haven't already seen that, and how to achieve 8 stars with Hubble. So good content as always. Thanks for coming, and I'll see you next time. Bye. Oh wait, are there any questions? I didn't check. Good morning, hello. Morning. Hi. No questions. Thanks for joining me. I'll see you next time.